Hey everyone, today I'm going to be going through the first video on ordinary differential equations. This case is the linear ordinary differential equation, okay? So I'm going to be deriving it and explaining where it comes from, and then in the next few videos I'll be doing a few examples on the linear ODE, and then maybe some Bernoulli type ODEs. And then eventually we'll work on to second order and etc. Okay. So, what is a linear ordinary differential equation? Okay, that's the first question. Okay, what is a linear ordinary differential equation? So, it's an equation of this type. Okay, so we have dy by dt plus p a function of t times y equals another function of t. Okay, what is this? Okay, so this y itself is just a y. Okay, and these pt's and gt's here, they're just continuous functions. Okay, so they could be sine. So for example, pt could be x squared, or it could, and gt could be sine t, just things like that. Okay, that's what these are. But they're, most importantly, they are continuous functions, so they don't have a jump in them, and you can draw them from you know. So a continuous function, quick dirty definition is a continuous function is a function in the form where you can just draw it from one side to the other without taking your hand off the page. Okay, it doesn't have any horrible holes in it. Okay, so that's what they are. Okay, and these y's are just y's. Okay, so this is what a differential equation is. Okay, it's just an equation in this form. Okay, and so the way we're going to solve this equation is we are going to assume there's a special function out there. Okay, there's a special function out there that this function, we're going to call it the integrating factor. We're going to assume for now that there's a special function that exists and it's called the integrating factor. Okay, and I'm going to say that the integrating factor is also a function of t. That's what the integrating factor is, but we don't know what that is. It could look like anything. Okay, but towards the end we're going to show you how we can obtain this function. Okay, towards the end. Okay, and this also is a continuous function. Okay, it's a continuous function that is also in the reals. Okay, so all these are pt, gt, and mu of t are all real functions. Okay, they're not complex, they're just real. Okay, so now we've assumed that this exists here. I'm going to call this equation. Okay, this is number one. We're going to take 1 and we're going to multiply everything in number 1 by mu of t. Okay, so multiply the left hand side and the right hand side. So what do we get? We get mu of t times dy by dt plus mu of t times p of t times y equals mu of t times g of t. Okay, that's what we obtain next. Okay, and so now this is where the key part comes into it. Okay, we're going to say, okay, by now we don't know what mu is, but we will show how to get mu at the end. But this is what we're going to say. Okay, this is the important part. We're going to say that when we differentiate mu, okay, we must obtain mu of t times p of t. Okay, that's the trick that we want from this function. Okay, when we differentiate it, we must obtain mu of t times p of t. So here's p of t, okay, and here's mu of t. So when we differentiate it, we want to obtain this part of the equation. Okay, that's the important part. That's what we want from this. Okay, so now we're just going to substitute. Okay, we're going to take this green part and we're going to substitute it in for this. Okay, so let's rewrite the equation number 1 again. So this is the same as mu of t times dy by dt plus, now we're going to substitute in mu prime of t times y, and this is equal to mu of t times g of t. Okay, so all we've done is we've taken this over here and we've substituted it in here. Okay, now what we're going to do now is, now we substitute this thing in. We're going to say, now see this equation here. This equation here that we have. This looks very familiar to something. So do you remember the product rule? So if we, so say we have two functions, product rule. So say we have a function x squared and times sine of x, okay? So this is a function of x, okay? Do you remember when you want to differentiate f of x, you have to take the first one, okay, x squared, and you have to differentiate that, and you have to multiply it by sine of x, so that's 2x times sine of x. Then you have to add it to the second one, so we have to add it to x squared times the derivative of the second one, sine of x, which is cosine of x, okay? So do you remember, so if you want to differentiate a function in a product form, you have to differentiate the first one, multiply it, then add it to the first one times the derivative of the second one, right? That's just the product rule, okay? If you're unfamiliar with the product rule, then I'd suggest you go and have a quick look up just around, type in the product rule and have a go at that, okay, before we get back to here. So this here, this equation, okay, star, this is essentially the product rule, okay? Because if you look at the left-hand side, what we have, we can rewrite the left-hand side, the whole left-hand side, we can rewrite this as mu of t times y, all differentiated, okay? Because these are just two functions. Y is a function of t, and mu is a function of t, okay? Y is a function of t, and because if you rearranged it, it would have t's in it, and mu is a function of t. So this whole left-hand side, you can just rewrite it as mu of t times y of t. And this is equal to mu of t times g of t, okay? Just the left-hand side, okay? So now we've got that, part of the equation. How can we go about getting a solution for y? Well, if we integrate both sides with with respect to dt, what do we have? We have the integral of this left-hand side, mu of t times y, which is a function of t, primed dt, equals the integral of this right-hand side, which is the integral of mu of t times g of t in dt. Okay, that's what we have here. But then, because of the fundamental theorem of calculus, because this is a derivative, these cancel out, okay? So these are going to cancel out here. Okay, so what then we have mu of t times y of t is equal to the integral of mu of t times g of t. And don't forget, dt, don't forget you've got a plus c hanging around here, okay? You don't want to forget out your plus c, okay? So here's my constant, okay? Right, but just for the sake of it, because it's a constant and I can take it away from both sides, I'm just going to rewrite, I'm going to rewrite this constant on this side, okay? Plus c here. Because this c can be anything, so okay? So I can just rewrite plus c. Really, I should write minus c, but it doesn't matter because it can be anything, okay? Now we have this form here. Now, how can we get y? Well, if we just divide, because it's a continuous function, and we assume that it's not equal to 0, otherwise if it was 0, we'd have just a trivial case of the equation. Okay, so mu of t is not 0, so we can just divide both sides by mu of t. And that will give us y, our solution. So this is the solution to the equation here. Okay, this is this whole solution to the differential equation. Okay, so this is t here. Sorry, my writing's awful. Okay, that's the solution to the equation. Now, as I promised, we have this solution, but the problem is we didn't know what mu of t was. But finding out mu of t is not too difficult because our first assumption was that, remember that original assumption was that mu of t, mu prime of t, remember when we said mu prime of t, it must be equal, if we got to here, remember we said it must be equal to mu of t times p of t, okay? That was our original assumption, okay? So then we can rewrite this, to get mu of t, we can write this as mu of t is equal to, mu of t is equal to, oh no, actually, let's rewrite this. Okay, we'll get p of t. Okay, on its own. P of t is equal to mu of t divided by mu prime of t. Sorry, divided by mu of t. Okay, that's what p of t is, right? But then if you notice that this here is what you get when you differentiate the natural log of mu, don't you? Because when you differentiate the natural log, you get the derivative over the original function, okay? So that's what you get when you differentiate the natural log. So the natural log of mu of t, differentiate that, you get p of t. Right, so in undoing this now, we get, so natural log of mu differentiated is equal to p of t. Okay, so then if we integrate both sides with respect to dt, there, we get that the natural log of mu of t is equal to, because it cancels out, the integral of p of t, okay, dt. And of course we have another constant hanging around, so instead of writing it on this side, I'm going to write it on this side, so we have plus c over here, okay. Now it's simple, because if we raise both of these functions to the power, okay, raise them, exponentiate them with respect to the with respect to e, we can get rid of the natural log, okay. So then we have e of the natural log of mu of t is equal to e of the natural log of the integral of dt plus c. And then of course these cancel on the left hand side, so you get mu of t is equal to e of the natural log of p of t, okay, dt plus c. So that is what mu of t is. And let me just remind you, pt is this thing here, okay? P of t is this thing here, okay? So just to recap, okay, our solution to the differential equation is this thing here. This is the solution here. This is the solution to the differential equation here, okay? But mu of t must obey this condition up here. And to get mu of t, we say mu of t is equal to e to the power of the integral of pt dt plus c. That's what mu of t is, okay? And if you substitute this back into the original equation, you'll find out that this plus c will cancel out. And so when you're integrating it, you don't have to worry about this, okay? So when we actually integrate it in the final solution, we don't worry about this plus c here because it will cancel out, okay? When we substitute this mu of t into our solution here. When we substitute it into here, the two mu's of t's, they'll cancel out, okay? That constant will cancel out, okay? So that's how you can solve this differential equation. That's where it comes from, okay? Thanks for watching. See you next time with some examples, okay?